Good morning.
Good morning.
So today I want to begin our discussion of Chapter 22. And Chapter 22 brings us back to carboxylic acids. We talked a little bit about carboxylic acids and their family in Chapter 19. And then we started to introduce some of the chemistry of the carbonyl group in general. Now, of course, a carbonyl group is embodied in the carboxyl group of carboxylic acids. And so we really needed this understanding to begin to proceed on. So today we're coming back to carboxylic acids, and we're going to talk about themes in carboxylic acid chemistry that involve the same type of reactivity that we saw with ketones and aldehydes. That is the ability of nucleophiles to add to the carboxyl group and to replace the carboxyl group. We're going to come back again later in a couple of more chapters where we start talking about carbon-carbon bond forming reactions and talk about Claisen condensations and other additions of carbon nucleophiles that are going to be based on this other property of carbonyl compounds, the acidity of the alpha proton. But right now we're going to just talk about the carboxylic acid family and their properties, the different members of this family, and their interconversion. And today we'll conclude by discussing the chemistry of acid chlorides and acid anhydrides, the two most reactive members of the carboxylic acid family. So let me draw out the family here, or at least the main members, the important players. Of course, we have carboxylic acids. And then sort of as a very close relationship, we have esters. We've already talked about the relationship between alcohols and water, and here in a carboxylic acid you sort of have half of a water molecule, and ester you have half of an alcohol molecule, so they'll have many things in common. Amides of various flavors. I'll just draw the amide structure generically with two sort of generic R groups. They can be alkyl, they can be aromatic, they can be hydrogens, and we have various flavors of amide, primary, secondary, and tertiary amide. We'll talk a little bit more about them. And these then moving along in the family, we have acid chlorides. Acid chlorides are very reactive. We'll be talking about their chemistry. I'm giving you the important members of the family. One could easily envision acid bromides, where the bromine is replaced with a chlorine, and perhaps envision very similar properties. In practice, they're much less commonly encountered, but very similar in their reactivity. Acid iodides, even more unusual and more reactive. Acid fluorides are a little bit funny. We're not going to talk a whole lot about them. They're still quite reactive, but actually a little less reactive than acid chlorides for reasons of resonance stabilization. Also, in the reactive members of the family, we have anhydrides, or sometimes you'll hear them referred to as acid anhydrides. And finally, and again, of course, I'm only taking a limited subset of the family, we have nitriles. And if you look at a nitrile is sort of the odd man out in this group, in the sense that you would say by comparison, I guess if I'm writing everything with S, I'll write carboxylic acids. By comparison, it doesn't look anything like the other members of the family. It's sort of the odd cousin. And what is in common to all of these is that the oxidation state of the carbon atom is the same in all of these. and all of these family members were in the +3 oxidation state for that carbon. So even though a carboxylic acid, an ester, an acid chloride, and an anhydride have carbonyl groups, carbon double bonded to oxygen, and the nitrile obviously does not, there are many similarities in reactivity. Also, when we talked about imines, I said that in many ways the reactivity of a carbon-nitrogen double bond is very similar to a carbon-oxygen double bond. In other words, imines have a lot of the same reactivity as aldehydes and ketones. And nitriles, now you have a triple bond, but again, you get this theme of a carbon multiply bonded, in this case triply, but otherwise doubly, to an electronegative atom. All right, let's take a moment to talk about naming compounds. And I don't want to get heavily caught up. I think it's very easy for students to obsess about nomenclature, and I want you to be able to see the forest from the trees. I really want you to be able to see the anatomical features of the molecule. In other words, be able to recognize the pieces of the molecule, because conceptually this is the key to understanding the molecules, and it's very easy to quickly end up getting yourself confused with rules of alphabetization and so forth. So here we have an ester, and an ester, as I just mentioned, has one component that comes from an acid and another component that comes from an alcohol. And just recognizing those two key components then is key to understanding their synthesis, some of their reactivity, and so forth. So let me take a specific ester and we can see how to name it. And so this ester has an acid component from butanoic acid and an alcohol component from ethyl alcohol or ethanol. So we call this ethyl. Esters get a first name and a last name. We call this ethyl butanoate. And it kind of makes sense on the nomenclature intuitively if you recognize that what we've done is just take the butanoic acid and replace the OIC with OATE. And so there, being able to see the components is important. I'll give us another example along the same lines. And so we'd call this compound methyl benzoate. That's OATE on the end because it's derived from benzoic acid. For amides, a lot of the thinking is kind of similar. We have two components, and we sort of recognize that here's our amide. And so we have a component that came from the acid and a component that came from an amine or ammonia. And so I'll give us a couple of examples here. In a way, you can think of this as being a parent compound in the sense that this is sort of the parent of any hexanoic acid-derived amide that would have a nitrogen on it, whether it had substituents or not. So we would call this hexanamide. And you can just think of this as basically putting amide on the end, so it's derived from hexanoic acid. So we call this a primary amide, because it's derived from ammonia because there are two NHs, two hydrogens on the nitrogen. And I'll give us an example of another amide. Let's, actually, I'll give us an example of a couple of more amides. So let me start on this blackboard over here. All right, couple more examples here. So this amide comes from acetic acid, so we would call this N-methyl acetamide. This compound is a secondary amide. And if you're typing out the structure, you would italicize the N. The N means the atom nitrogen. It means that there's a methyl group on the atom nitrogen. So unlike the lowercase n when I talked about, say, N-butyl lithium, which meant normal, it meant the linear chain, a capital N, as I said, typeset in italics, but probably just written like I've written it here, means on the nitrogen atom. Take another example here. Common amide, an amide that's often used as a solvent, is NN-dimethyl formamide. So we have two substituents on the nitrogen, so we call this NN-dimethyl formamide, all one word. It's a tertiary amide. In other words, it has two substituents on the nitrogen. And one thing to keep in mind, many students look at a compound like dimethyl formamide and they say, oh, it's an aldehyde because I'm used to the CHO group. Well, the nitrogen and the carbonyl function together as a pair. They work as a functional group. In other words, we see a functional group. You know, one of the driving concepts in organic chemistry is that groups of atoms closely connected also often have very specific properties. Because the nitrogen is conjugated, because it's in resonance, and I'll talk more about that in a moment, because it's in resonance with the carbonyl group, this behaves like an amide, not like an aldehyde in all of its reactivity. So just as methylacetamide, N-methylacetamide is not a ketone, NN-dimethyl formamide is not an aldehyde.
Is the name aceto and forma like a proper iron?
Ah, okay, great question. Are these the proper names or are these the common names? Anyone want to answer? Common. Yeah. So this one would be N-methylethanamide if I wanted to write out the IUPAC name, just as we had done there with hexanamide, but no self-respecting chemist would call it that. The latter one would be NN-dimethyl methanamide because it's derived from methanoic acid, but everyone calls it formic acid.
Wait, then would it be all right if we put this instead of the IUPAC name on the test?
As I said, students often obsess over nomenclature. You would be hard, no, it's okay. And it's scary. It's scary because I literally can hand you a book, 500 pages, on how to name organic compounds, and it's easy to obsess over it. The other reason it's easy to obsess over this is because when it comes down to it, this is simple. I don't mean it's simple to know all of the rules, and some of them are arcane. I mean it's something that a computer can easily work through, and there's very little higher thought process involved in naming a compound. And so it's easy to spend time obsessing over that and not to get on to the stuff that's really conceptual. So don't worry, I won't ask you on a test, was that the IUPAC name or the common name? All right. Now, I'll give you one thing that I wouldn't expect you to obsess over, but I was obsessing over just to show you one other example of where we have two different substituents here. So this is another tertiary amide, and for this particular one, it actually was an example from your book. It's N-isobutyl N, and I'm going to break it with the hyphen here just because I can't write it all out on one line. N-methyl, and then what's our carbon chain? 1, 2, 3, 4, 5, pentanamide. I think your textbook must have had butanamide, so I'm going to draw it with one fewer carbon here. Butanamide, and that was an example from the problems that I ask you to work out as you go along when you're working things out. Anyway, what we've done here is we've named the two halves on the nitrogen and we've alphabetized it. But again, I think it's really, really easy to end up obsessing over that, and don't get that obsessed. All right, let's go on to acid chlorides and acid anhydrides. All right. So let's go on to an acid chloride here derived from pentanoic acid. And again, we're seeing the family relationships here too. This is an acid chloride derived from pentanoic acid. So we call it pentanoyl chloride. We've taken the pentanoic of the acid from which it's derived, and we've changed it to OYL. With the common names, you do it slightly differently. So this compound here is acetyl chloride rather than acetoyl chloride, and it's just how people name it, how it flows off the tongue. And let's do one more. I'll do an anhydride here. This is the anhydride derived from benzoic acid. So we call it benzoic anhydride. All right. Last class of compounds I want to talk about in the family is nitriles. And so I'll just take the nitrile that's related to hexanoic acid, the one that has 6 carbons in it. You might draw it with C triple bond N. You might draw it just as CN. It's the same thing. This is called hexane nitrile. So since it's a 6-carbon chain, it's called hexane, and you just put nitrile on it. You don't have to specify the position of the nitrile because being triply bonded, there's no other place that you could put that nitrile group except on the end of it. Again, the small molecules tend to have common names. We also tend to splash the small molecules around like water in the laboratory. Acetonitrile is a common solvent. This is acetonitrile. Acetone is a common solvent. Acetic acid is a common solvent. And so you splash them around in separatory funnels and in chromatographic columns and the like. And let's see, I'll give you one more example. So one of the things that we saw when we were talking about naming carboxylic acids was we said when you have different groups, some of them will have lower priority. So in general, carboxylic acids have higher priority than ketones and aldehydes. And nitriles have lower priority than carboxylic acids. So if you have if you have a nitrile group and an acid group, you end up naming it as the substituted acid. So this one is commonly called cyanoacetic acid. All right, well, that gives a kind of a quick overview of how we talk about these compounds. I want to talk now about their physical and then their spectroscopic properties, because I think that gets us into things that are more interesting and more important. Your textbook sort of approaches this from the point of generalities, and I decided I would approach our discussion today of the physical properties of compounds from a couple of specific examples that were kind of important compounds. So, and this is maybe giving you a little bit of a flavor of my own thinking about the chemistry of the carboxylic acid family. So I decided to start our discussion today with ethyl acetate. Ethyl acetate is, of course, a widely used solvent. It's present in nail polish remover. You may have used it for liquid-liquid extraction in the laboratory. Esters in general tend to have rather nice fruity odors, and so ethyl acetate has a strong smell to it that's not unpleasant. Some of the esters, like isoamyl acetate, have very strong fruity odors, so that's just overpoweringly banana. It's one of the components in banana. So ethyl acetate is a liquid. It has a boiling point of 77 degrees Celsius. And I thought that might be a nice kickoff point to kind of contrast some of the properties to other molecules. And so when I was thinking about molecules that are kind of the same size, I figured, well, ethyl acetate has 6 heavy atoms, 6 carbon and oxygen atoms. It's about the same molecular weight as hexane. So by comparison, I'd say hexane is a liquid. 69 degrees is its boiling point. And then if you say, well, we learned when we talked about van der Waals contacts that if you have a more linear molecule, you get more van der Waals contact. And of course, ethyl acetate sort of has a branch in it. You might say maybe it would be a better comparison to compare it to 2-methylpentane. And 2-methylpentane is also a liquid. And it has a boiling point of 60 degrees. And so the take-home message on this is, not surprisingly, ethyl acetate has a higher boiling point than molecules of similar size that don't have dipoles in it. And it should make sense. I mean, you have a molecule that has a molecular dipole in it. And as a result, you also see differences in solubility. And all of this really can be explained by thinking about resonance structures. So I'll just add that the solubility is, it's soluble in water, soluble to the extent of about 8.3 grams per 100 milliliters. And I always find that sort of interesting. I mean, on the one hand, you expect ethyl acetate to have solubility in water. We've learned that if you have polar atoms and you have a reasonable ratio of polar atoms to carbon groups, you should have some solubility in water. And at the same time, you may have heard the number 4, that if you have 4 carbons per oxygen or fewer, you can think of something as soluble. But here, in a way, we have 2 carbons per oxygen. And so you think about something like ethanol, and it's miscible with water. It mixes with water, so 2 carbons, 1 oxygen. Diethyl ether, 4 carbons, 1 oxygen is about the same solubility in water, but here we have 2 oxygens. Tetrahydrofuran, 4 carbons and 1 oxygen is completely miscible with water. So in a way, it surprises me. It's a little less soluble than you might think. And we certainly can think of it as polar, and you can think of it either as, oh yeah, the bond between oxygen and carbon is polarized, and so you can think of it as saying delta plus, delta minus, or you can think of its behavior in terms of resonance structures. And so just as with every carbonyl compound, you can write minor resonance structures in which a minor resonance structure in which charge is separated like so. And I guess I'll be a good person in drawing my lone pairs over here. What's interesting about ethyl acetate and all other esters is you can write a second resonance form like so, with a positive charge on this oxygen. And so collectively, the major resonance structure and the minor resonance structures, the small contributors, certainly can explain the polarity of the molecule, just as we saw and explained that acetone had a higher boiling point than, say, isobutylene. And yet, there's a little bit unsatisfying why it's not more polar. The one thing that these resonance structures don't really embody is the fact that this oxygen is, while it's donating electrons through resonance, it's also pulling them away in the sigma bond. So in other words, we have these 2 oxygens pulling in opposite directions through the sigma bonds to pull electrons away. And for that reason, ethyl acetate isn't as polar as you might otherwise think. In other words, it's soluble in water, but it's not super soluble in water, or not miscible in water. It is a polar molecule. It has a dipole moment to it, but the dipole moment is not huge. It's not huge as, say, dimethylformamide, which I'll talk to you about in a moment when we talk about amides. All right, I want to contrast ethyl acetate. As I said, I'm coming at this from the point of view of specific molecules and their properties and sort of what they mean to me. I want to contrast ethyl acetate to a couple of familiar amides. And so I'll start with acetamide. And so acetamide, by comparison, is a solid. It's got a melting point of 82 degrees, and if you heat it enough so it boils, it has a boiling point of 221 degrees. So clearly acetamide, even though it's a smaller molecule than ethyl acetate, is much stickier. And we saw this principle in carboxylic acids when we talked about their high boiling points. Acetamide has the ability to hydrogen bond, and so you can form hydrogen bonded dimers, and you can get further hydrogen bonding because you have the electronegative nitrogen bound to the hydrogen, and so that can make these molecules stick together. Now, dimethyl formamide, of course, doesn't have hydrogen bonding. You don't have any hydrogens on nitrogen. And so dimethyl formamide can't participate in hydrogen bonding, and yet it too is much higher boiling than ethyl acetate. So dimethyl formamide is a liquid. Its boiling point is 153 degrees. It decomposes to carbon monoxide and methylamine at that temperature, so you can't really distill it. And it's much more polar. It's got a bigger dipole moment, a bigger dielectric constant than ethyl acetate. It's miscible with water. And you really, in the case of dimethyl formamide, can think of it getting a lot of its properties from that minor resonance structure off on the right. I'm not going to write off all of the resonance structures. I'm just going to write out the key resonance structure here and say you can explain a lot of its behavior by this type of resonance structure. Now, this brings up an important point about amide. So this is still a minor resonance structure. But the point is, the molecule is always, I'll get to your question in a second, the molecule is always multiple resonance structures all at the same time. These are just different pictures of the same thing. But in the case of ethyl acetate, it's just a little bit of this resonance structure. And in the case of dimethyl formamide, it's a little bit more. It's on the order of maybe 30% of that resonance structure if you needed to have a number in your head. One of the things that's very important to keep in mind about this fact is the fact that this nitrogen in dimethyl formamide and in amides in general is much closer to being sp2 in its properties, to being sp2 hybridized than sp3 hybridized. I'm going to write it as sp2 hybridized here, because that really comes like as the closest description. It's somewhere in between, but it's more like sp2 hybridized. In other words, that nitrogen is not basic like an amine. It's much less basic than an amine because it's participating in resonance. All right, I saw a question first.
What does it say behind the...
Decomposes. DEC is often the shorthand you'll see chemists write for decomposes. Another question.
Yeah, back to that top of the boiling point
Of 2-pentanone. 2-pentanone, let's see, it's acetone boils at, I think, 56 degrees, so we're talking somewhere around 80-ish. Oh, wait, pentanone, so I'm thinking butanone. So pentanone, yeah, close to 100 degrees. So yeah, I mean, even a bigger dipole for there. But the point is, if you look at 153 versus 77, it's a big difference. So in other words, ethyl acetate's a polar molecule, but it's not like a superpolar molecule. And by the time we come to the amides, it really is, quite polar. If I wanted to make maybe a closer comparison to ethyl acetate, Maybe I could also say NN dimethylacetamide just because, let's see, here we have 4, 5. I guess that's a reasonable comparison here. Other questions? All right, I want to take a look at this point at what the IR spectra tell us about the behavior of these molecules, in part so you can get used to recognizing them, and in part so you can continue this theme of understanding their properties. All right, so to separate the forest from the trees, we talked before about all the carbonyl compounds. We talked, well, except amide. No, I guess we talked about amide, so except acid chlorides and anhydrides. We talked about esters and aldehydes and acids and ketones and amides and their relative carbonyl stretches. And the main point is you have a carbonyl band somewhere around 1700 wave numbers. And they differ a little bit depending on the nature of the particular carbonyl compound. So amides have their carbonyl typically around 1660, somewhere below 1700 is typical. Typically, I'll sort of take a middle ground of around 1660. And so if we compare this, I always like to think of, when I hold things in my head for understanding them, I always like to think around one compound. It's kind of the same that you saw in the theme of my talking about ethyl acetate or dimethyl formamide. So if I think of a typical ketone, whether it's cyclohexanone or acetone, I sort of think of a typical ketone as having about 1715 wave numbers. And so you think about this, and you'd say, well, this is saying that the carbon-oxygen double bond stretch is weaker than that of a ketone. So I'd say a weaker CO. And you think about this resonance structure, and this minor resonance structure really helps explain that very nicely. In other words, of course, it's not one, it's not the other, it's both and other resonance structures at the same time. But if you look at this, you say, oh yeah, I can understand. We have some single bond character mixed in here with the double bond character. So instead of vibrating at a higher frequency like a stiffer spring, it vibrates at a lower frequency, ever so slightly lower, like a less stiff spring. Now, if we come over to esters, typical ester, and again, these are sort of generic compounds and generic values. The typical ester is at about 1735 for the carbonyl stretch. So you don't see it very, very different from a ketone, just a little bit different. But where you really start to see things different is by the time you get to acid chlorides and acid anhydrides. And this is where I think it's really telling. So you look at an acid chloride, and the carbonyl stretch now is at about 1800. And if you're looking at an IR spectrum, 1800 is really distinctive. In other words, 1720, 1735, you'd say, okay, I can see differences, I can read the scale, but they're all sort of similar. Amide, you'd say, oh, 1650, 1660, 1670, you'd say that's significantly different. Then at the other end, you look and you'd say 1800, that really starts to look different. And one of the ways you can think about this, there are a couple of ways you can think about it. So obviously the fact that we're at 1800 means here we have a stronger CO bond. And one way you can think of it is without resonance. You can say, well, chlorine is electronegative. You can say chlorine is electronegative. It has a Pauling electronegativity of 3.2. And it's basically pulling electron density down. And the big difference between chlorine and oxygen is the same row as carbon. Oxygen can give good resonance overlap with carbon. Chlorine, instead of being second row, is third row. It's one row down. You can't get much pi bonding. You end up with very little double bond character, but a lot of that sigma electron withdrawing character, a lot of the chlorine inductively electron withdrawing. And so you can think of the chlorine as pulling electrons down from the oxygen, making this bond stronger. It's pulling electron density down. You have lone pairs of electrons. They're pushing back in. I like to, in the back of my mind, I probably wouldn't write this resonance structure, say, elsewhere, but in the back of my mind, I kind of keep in mind the fact that if you take that type of thinking to its logical extreme and say, all right, there is a component of the chlorine pulling electron density away inductively, you can think about this non-bond resonance structure here. And in this non-bond resonance structure, you have some triple bond character. In other words, this is a very minor contributor, but it's basically that oxygen pushing in extra electron density, making that carbonyl bond even stronger. If it's stronger, you have it resonate at a higher frequency, and so you end up at 1800 instead of 1700 wave numbers. It's also very hot electronically, and we're going to see that acid chlorides are the most reactive member of the family with nucleophiles. Now, you have the same type of principle in acid anhydride. So just like the chlorine is pulling away electron density, you have the acyl group is pulling away electron density. And for that reason, in acid anhydrides, the carbonyl stretches also come at a higher frequency than you might expect for, say, a ketone. And acid anhydrides show pairs. 1820 and 1760 would be typical for a pair of bands in the IR. In other words, you have two stretches, not one. And at first you might say, oh, well, that means that there are two types of carbonyl groups. It's not really that simple. When you have vibrations and they're close together, you get what are called coupled vibrations when they're close to each other in space. Kind of like splitting in the NMR spectrum. And when the vibrations couple, you have them working together. In other words, it's not one carbonyl stretching and the other carbonyl stretching, but it's both of them stretching together. And there are two types of stretches. One of them is an asymmetric stretch, and one of them is a symmetric stretch. So you end up with two bands. All right. And so I think what the IR spectra really are telling us is that acid chlorides and acid anhydrides are really special in their properties. And they're special in that you have a lot of extra electrophilicity at the carbonyl. In other words, acid chlorides and acid anhydrides react with many different electrophiles because that carbonyl has the pulling away, the electron withdrawing group of the acyl group or of the chloride group. So to put it bluntly, if I take acetyl chloride and I pour it into water, it sizzles, spatters, it reacts violently. And the reaction gives acetic acid and HCl. Acid anhydrides also react with water, not as violently, but they react. I'll just write reacts by contrast to violently. And acetic anhydride hydrolyzes. Hydrolyzes is a fancy way of saying cleaves, lyses by water. And where I really want to compare this to start our discussion of the chemical reactivity, of the chemical properties of the carboxylic acid family, where I really want to contrast things to is to start to contrast them to, say, esters and amides. So if I take ethyl acetate and water, there's no reaction. We'll learn later how we can hydrolyze ethyl acetate with water, but it doesn't occur by just mixing ethyl acetate and water. I can qualify that. It can occur over a very, very, very long period, like years, or it could occur if you boil the ethyl acetate in water, but for all intents and purposes, there is no reaction. And that's a very good thing, because esters and amides, which I'll write as the next molecule, I'll write NN-dimethylacetamide, these are the molecules of biology, not ethyl acetate and NN-dimethylacetamide, but of course esters make up your lipids. The membrane that covers every cell in your body is made of lipids. It's made of long-chain fatty acids that are esterified to glycerol that are hooked to other fragments like acetylcholine. And what would happen if at room temperature, at 37, at body temperature, esters reacted with water, is your cells would all break apart. So it's very fortunate that esters don't without a catalyst or an enzyme, react with water at any appreciable rate at room temperature at 37 Celsius. Amides, it's the same thing. If I take an amide with water, there's no reaction. And again, this is very, very important because all of the proteins in your body are made up of amides. And if they were to react with water and the proteins would break down, you'd just be a pile of amino acids and fatty acids and glycerol. And you wouldn't be you. Now, amides and esters are also widely prevalent compounds, not only naturally, but synthetically. Your nylon backpack is made of a polyamide that chemists made to mimic proteins, and initially the protein silk, because stockings, as I see you're wearing, used to be made only available in silk. And silk is expensive and fragile, and at the time of World War II was needed for the war effort, and so having synthetic substitutes was useful. Esters, again, very good thing that polyamides, like your backpack, don't hydrolyze. When it rains, your books would fall out and get wet. And polyesters, in addition to polyester fabrics, if you're wearing a polyester warm-up jacket there, are used to make your water bottles and your plastic, that's probably polystyrene in your container up front, but your water bottles that you buy, the Aquafina or whatever horrible water they sell on campus here, are made of esters. And again, you'd be in a lot of trouble if they hydrolyzed on their own.
Would the amide and the ester reaction go forward if we apply some acid to the reaction?
Would the amide, yes, and we will talk about that in our subsequent talk here. So yes, indeed, acids and strong bases can make them react. I want to finish one discussion of spectroscopic properties before moving on to chemical reactivity and focusing on acid chlorides and anhydrides. And I want to conclude maybe by talking about acetonitrile here and nitriles in general. So we talked about all the carbonyls, and we said carbon-oxygen double bonds are centered around 1700 wave numbers. Triple bonds are, of course, stronger than double bonds. A carbon-nitrogen triple bond is centered at about 2250 wave numbers. They're usually sharp in the IR spectrum. As long as we're talking about acetonitrile, I'll add also no reaction with water. And again, that's in the absence of strong acid or strong base, and we'll be talking about that later. I also want to give you a generalization. Remember, we were talking about NMR before, and I said I like to have a few baseline numbers in my head. The methyl group, whether it's on an acetonitrile or next to any sort of carbonyl, these methyl groups are always about 2 ppm, very close to 2 ppm in the 1H NMR, in the proton NMR. And the reason I like to keep that number in mind is then I can think, okay, if we have a methylene, it's just like a methylene in an alkyl chain is a little further downfield, a few more tenths downfield than a methyl group, and a methine in an alkyl chain is a little further downfield. We can go a little further downfield. So in general, you can say for a hydrogen that's next to a carbonyl or next to a nitrogen, in general, about, let's say, 2 to 3 ppm or 2 to 2.5 ppm, depending on how you want to look at it. In other words, a methylene, a CH2, is going to be a few tenths further downfield. A methine will be a few tenths further downfield. I don't want to get overly caught up on the numbers here for spectra. I just want to mention a few things. In the carbon-13, carbonyls in general are way downfield of the amide region, of the aromatic region. So in general, you can pick out carbonyls. Carbonyls and ketones and aldehydes typically are around 200 ppm, a little bit more, 220, 190, somewhere around there. Typically for the whole carboxylic acid family, we're talking about 160 to 180 ppm in the C13 NMR for the whole sort of carbonyl, the whole carboxylic acid family. And just for the sake of completion, I'll give you nitriles. You have a carbon-carbon triple bond. It's kind of like an alkyne, but you have an electronegative atom. So you're talking about 115 to 120 ppm. All right. Organic chemistry is about making stuff, at least a big part of it. And there are chemical reactions to interconvert all of the members of the carboxylic acid family. Acid chlorides, acid anhydrides, esters, carboxylic acids, amides, and even nitriles can be interconverted to other members of the family, to nitriles, to esters, to carboxylic acids, to acid chlorides, to acid anhydrides. Now, if I were to say, okay, how many different, just if I figured one reaction for each of these, and I think I've named 6 members of the family going into any other 6 members of the family, I basically would end up having a minimum of 15 different reactions, and there are, of course, more, to interconvert these members of the family. And so the first thing you might think is, oh my God, this is overwhelming. How can I possibly understand all of these reactions, all of these reagents? And the answer really becomes by thinking mechanistically, understanding the principles, and understanding the general reactivity of different molecules. So I want to give you some generalization here before we dive into specifics. And so if we have some general member of the family, and nitriles are kind of the oddball, so I'm going to leave them out. We'll talk about them at the end on the next lecture. And we have some nucleophile, Nu minus or NuH, sort of a very, very generic type of species. Water, of course, was NuH. It was OHH. In general, a common theme is that the group on the carboxylic acid can, under some conditions, get replaced. It can get displaced by a nucleophile. And if I'm going to write a balanced equation, I would also say plus X minus or HX. And that's not meant to be a functional equation at this point. This is meant to be a generalization, and now I want to start to put structure and some specifics to this. And so what I would say is this occurs with basic nucleophiles. So in other words, species like alkoxide, RO minus, hydroxide, HO minus or OH minus, and let's say amines. I'll write it as R2NH, but I'm not meaning specifically a secondary amine. I could mean a primary amine, or I could mean ammonia. Or, so in other words, in general, members of the carboxylic acid family in general can react with basic nucleophiles, or with good electrophiles. And of course, what do I mean by good electrophiles? Well, good electrophiles are those ones that sizzle or react vigorously with nucleophiles. So specifically in this family, I'm talking about acid chlorides and acid anhydrides. So that's sort of one generalization that I'd make. And the other generalization that I would make is that weakly basic nucleophiles and what do I mean by weakly basic nucleophiles? Well, we talked about these with ketones and with aldehydes. We're talking about things like alcohols and water. So I'll write ROH and water. And I'll say that they can react with less reactive electrophiles. And what do I mean by less reactive electrophiles? Well, I mean the members of the family that don't react with these that don't have that electron withdrawing group, that don't have that carbonyl shifted up to 1800 or thereabouts in the IR spectrum. So we're talking esters, acids, amides, and nitriles. And they can do this if they have some help with strong acid catalysis. And what we're going to see in the next lecture is that a strong acid can protonate the carbonyl of an ester or a carboxylic acid or an amide, or can protonate a nitrile group and take something that's only a weak electrophile and turn it into a strong electrophile in a mechanism that we end up going through. All right, so that generalization serves as a framework, and now I want to go on to some specifics and to talk about specific reactions of acid chlorides and acid anhydrides. And so by way of a specific example, I'll take acetyl chloride, and I want to write a balanced equation here. Acetyl chloride, let's look at its reaction with a simple amine, methylamine. Acetyl chloride can react with 2 molecules of methylamine to give dimethylacetamide. And organic chemists are always bad about balancing equations, but I will balance it. And dimethyl ammonium chloride, dimethylamine hydrochloride, Me2NH2 plus Cl minus as a salt. What I want us to be able to do, because this is the archetype for all of our thinking about this chemistry, I want us to be able to think and understand our way through these mechanisms, and particularly to get the big picture, because sometimes the details aren't going to be that important. So here's our acetyl chloride. We know that that carbonyl is electrophilic. And we know that dimethylamine is nucleophilic. It has a lone pair of electrons. It's willing to share those electrons. We can attack, very much like the theme we saw in imine formation chemistry. We can attack this extra electrophilic carbonyl. And at this point, I'm going to write this as irreversible. And it's always a little bit of a judgment call. But if you have something where you're really, I guess I can write the first step as reversible, although honestly, I'm not going to sweat about it. So I'm just going to write this one way. Okay. So at this point, though, the big picture, the big idea is now, just as in imine formation, at this point, we formed a tetrahedral species. We formed a tetrahedral intermediate. And this and the next step really become the big idea here, the next part of the reaction. Yes? Oops, did I forget an H? No, I drew in an extra lone pair. You mean here? Ah, wait, where? Oh, okay. I was meaning to, I'm sorry, I was meaning to draw in dimethylamine. So let's do 2 molecules. We could do it with methylamine, but let's do 2 molecules of dimethylamine react to form the dimethylamide and dimethylammonium hydrochloride, dimethylammonium chloride. And let's have our 2 methyls on the nitrogen with a hydrogen and a lone pair, add to the carbonyl, attack to give a tetrahedral intermediate. And the big point about this is our tetrahedral intermediate is going to be unstable, just as we saw in imine formation where the hemiaminal is not a stable compound, it's not an isolable compound. That same theme emerges here. Question? Yeah.
Why do we need two equivalents?
You're going to see. Why do we need 2 equivalents? Great. All right. Just as in imine formation, your tetrahedral intermediate is unstable. I'll be a good person for 1 moment here. And I'm going to draw in all of my charges and all of my lone pairs of electrons. The tetrahedral intermediate can break down. It doesn't stick around. It can kick out chloride. Chloride is a good leaving group. Chloride gets expelled. But remember, this nitrogen here in an amide is not an amine nitrogen. It is not a basic nitrogen. It is not an sp3 nitrogen. It doesn't want to have a proton on it. It is very acidic, and it's going to give up that proton to anything that's basic. And we have dimethylamine present. And so our dimethylamine is the strongest base in the house. And dimethylamine is going to pull off that proton to give you your dimethylacetamide plus dimethylammonium chloride. Well, I guess I've already written my chloride, so I'll just balance my equation and say plus the dimethylammonium product. And if I were to not have that extra equivalent of dimethylamine around, halfway through all of my dimethylamine, the remaining dimethylamine would be protonated as the hydrochloride. Now, the reason I'm saying not to get too bent out of shape on this mechanism, the big picture, nucleophile attacks, we get a tetrahedral intermediate. The tetrahedral intermediate breaks down, protons shuffle around. Your textbook writes these 2 steps in reverse, or more specifically, your textbook on closely related reactions, and in the homework, writes the deprotonation step at the tetrahedral intermediate. I don't think that makes as much sense on the basis of acidity. Don't get bent out of shape about it one way or another. The big picture, nucleophile attacks, tetrahedral intermediate breaks down, protons shuffle around. If they shuffle around beforehand, it's not that big a deal. Other big picture item, from a synthetic point of view, chemists often want to go ahead and not waste a valuable amine. Sometimes they'll add a base that's sacrificial, a tertiary amine like triethylamine or pyridine is added as a base. I'll write parenthesis pyridine here, is added as a sacrificial base, so you can use only one equivalence of amine. All right. this same basic principle of reactivity of acid chlorides applies with all other species, whether it's strong base, whether it's basic nucleophiles like amines or weakly basic nucleophiles like alcohols and water. Acid chlorides react vigorously. So for example, if I take benzoyl chloride and I take ethanol, they react just like I said, acetyl chloride reacted to form with water. They react to form an ester, ethyl benzoate. And again, if I want to balance my equation, HCl would be a byproduct. Very often in this chemistry as well, often you'll use pyridine as a base. Pyridine triethylamine can be used as well, diisopropyl ethylamine as well, to react with the HCl. So just for the sake of writing a balanced equation, if I take my benzoyl chloride plus ethanol plus pyridine, I'm going to go ahead and get ethyl benzoate plus pyridinium hydrochloride. And on a preparative level, in the laboratory, you would probably carry out an aqueous workup in a separatory funnel in which you would extract the ethyl benzoate into the organic phase. You would wash away the pyridinium hydrochloride salt in the aqueous phase, and then you would dry your organic phase over mag sulfate and filter and concentrate to get your ethyl benzoate. You can imagine all sorts of other reactions of acid chlorides. We already saw that acetyl chloride reacted with water to give acetic acid, or you could use some sodium hydroxide in there to get ethyl acetate out of there, sodium acetate out of there. You could react sodium acetate with acetyl chloride to get acetic anhydride. And so maybe I will just very quickly sketch out these reactions. Acetyl chloride plus H2O goes to acetic acid plus HCl, acetyl chloride. And you should be able to think your way through mechanistically on all of these. Acetyl chloride plus 2 hydroxide anion goes to acetate anion plus water, H2O plus chloride anion. And I'll just write one more balanced equation, acetyl chloride plus, let's say, sodium acetate, just for the hell of it, I'll write in a counter ion here, goes to acetic anhydride plus sodium chloride. All right, as disparate as all of these reactions sound, they're actually all the same basic principle. Once you get the idea of a nucleophile attacking your acid chloride to form a tetrahedral intermediate, the tetrahedral intermediate breaking down and some protons shuffling around, you end up comfortable with all of this chemistry, and you see that it really, really falls into the same category. Now, I wanted to mention two last points. One of these is the trends we've been talking about. We said that acetyl chloride is more reactive, or in general, I'll write acid chlorides are more reactive than anhydrides, and those are more reactive than esters, and those are more reactive than amides. And that makes sense if you consider the pKa of the conjugate acid of the leaving group. In other words, HCl is the conjugate acid of chloride as a leaving group. Its pKa is -7. In other words, chloride is a very good leaving group, even in this addition elimination chemistry. The pKa of a carboxylic acid, the conjugate base of a carboxylate leaving group in anhydrides, is on the order of 4 to 5, while it's much less of a good leaving group than chloride. And remember, this is addition elimination chemistry, not SN2 displacement chemistry. It's still a good enough leaving group. By the time we come to an alcohol, the conjugate base of alkoxide leaving group, we're talking pKa 16 to 17 here. Now we're not so good. And then by the time we come to an amine as our leaving group here, now we're at about, depending on which number you use from your textbook, about 38. And so now we've basically spanned 5 orders of magnitude here in our peak, spanned, pardon me, almost 50 orders of magnitude here, 45 orders of magnitude in our chemistry here. All right, the only sort of oddball in this mix are carboxylic acids. And the reason I haven't immediately included them is there's one special caveat. You'd say for many purposes, and we'll see in Fischer esterification and transesterification, esters, carboxylic acids are the same. But in the case of a base, often you will have a base deprotonating a carboxylic acid to give you a carboxylate, and then you end up really, since the carboxylic acid is acidic, you really have to think about O2 minus, which is just not a leaving group. So there are certain cases where you're talking about, say, an ester will react with an amine if you warm it, but a carboxylic acid is just going to do proton transfer with an amine, unless you heat the absolute hell out of the thing to hundreds of degrees. All right. Last thing I want to do is talk about the reactivity of anhydrides. And really, for many, many purposes, the reactivity of anhydrides is like that of chlorides, acid chlorides, except they don't sizzle with water. So they're less reactive. So if I take acetic anhydride and dimethylamine, and again, I'll write a balanced equation, I get dimethyl acetamide, and I also get plus dimethyl ammonium acetate. By the way, you will often see this written as acetic anhydride AC2O, and sometimes you'll see it written here as an AC group, but hence I'm just writing it here as OAC. Now, for this same reason and the same idea we talked about when we were talking about the chemistry of acid chlorides, because you're using a second equivalent of amine as a base in this chemistry, because it's getting protonated by the acetic acid byproduct of reaction, often you will use a sacrificial base like pyridine. So I'll write a balanced equation, and at this point I'll use the shorthand for acetic anhydride. So I'll write acetic anhydride plus methylamine plus pyridine. Often you would see these as reagents written above an arrow, goes to AC, same product here. And then if I want to write a balanced equation, I'm going to get pyridinium acetate as my byproduct. And all of these principles of reactivity then apply to things like alcohols as well. So if I take acetic anhydride and ethanol, and again, I'll just use this common shorthand for acetic anhydride, plus ethanol, just as we saw it reacted with water to give acetic acid, acetic anhydride reacts with ethanol to give ethyl acetate. And again, there are many ways you could write ethyl acetate. I'll just write it here, OET, plus ACOH. All right, so I think that gives us kind of an overview of the reactivity of the most reactive members of the family, the acid chlorides and anhydrides, as well as the general properties of the family. We'll talk about the reaction of acid catalyzed reaction with weak nucleophiles for esters and carboxylic acids, as well as the effect of strong nucleophiles like bases on them next time.